So section 6.3 is definite integrals and antiderivatives. So we're going to cover half of this section today. So rules for definite integrals. A definite integral is an integral that is calculated between two limits of integration. So the zero property. If I integrate from a to a, the derivative or the integral, the area under the curve, will be zero. In other words, if I have a curve and I integrated from a to a, there is no width, so there is no integral. The integral is zero. The additive property. If I take the integral from a to b, and then the integral from b to c, and if I evaluate those separately and then add them together, I will have the integral from a to c. Order of integration. This one's a little bit tricky. If I integrate from a to b, I get a certain integral value. If I integrate from b to a, okay, I'm sorry, they started with b to a. If I integrated from b to a, from here to here, that would be the opposite of integrating from a to b. So when I integrate from left to right, I will usually get a positive integral. When I integrate from right back to the left, and I know this doesn't make a whole lot of sense right now, but once we start to use our algebraic means for integration, you'll see that we get the opposite value. A constant multiple. If I have a function and I multiply it by k, the integral from a to b of k times the function is the same as finding the integral first and then multiplying by k. I'll give you an example of this. If my function looks something like this is my just my f of x. If I multiply that function by k, I'm going to get a different integral that will be k times the first. If the constant multiple is negative, we just bring the negative sign out front. So for any number k, we write the k out front. If it's a negative, we just write the negative. It's the same thing. Sum and difference. The integral from a to b of one function plus or minus another function is the integral of the first function plus or minus the second. In other words, not only can I break up the integral into different limits of integration, but if I have two functions added together, I can break the integral up into each function separately. Max and min inequality. If the maximum f and the minimum f are maximum and minimum values of f on AB, then, so let me draw a picture. So I'm going to integrate from A to B, and within that I have a maximum and a minimum value. If I take the minimum value of the function and multiply it by the width of the function, that will be less than the entire integral, which will also be less than the maximum value multiplied. So you can see that the minimum value gives me a small rectangle, and the maximum value gives me a large rectangle, and the actual integral is in between the two. Okay, domination. If I have two functions, and if the function f of x is higher than the function g of x on the entire interval, then the integral of f of x will be greater than the integral of b of x. Same way, if the function is greater than 0 on the entire interval, then the integral will be greater than 0. So let's do some examples. This says example using the rules for definite integrals. So suppose we know that the integral from -1 to 1 of f of x is 5. In other words, the area under this curve between -1 and 1 is 5 units. And the integral from 1 to 4 of this function is -2 units. That tells me that from -1 to 1, my integral is above the x-axis, from 1 to 4, it is below the x-axis. And a different function has a definite integral of 7 between -1 and 1. So using my properties, can I find the integral from 4 to 1? Well, from 4 to 1 is these two added together, but working in reverse. So if I take the integral from 4 to 1, whoops, I'm sorry, it's not the sum, it's just the one integral. If I take this integral from 4 to 1 instead of 1 to 4, it's the opposite of -2 or +2. Find -1 to 4. So -1 to 1 and 1 to 4, all I have to do is add those together, and I get 5 plus -2, or 3. The last one, find the integral from -2 to 2 of h of x if possible. I don't know anything else about h of x but the fact that from -1 to 1 it is 7, so this is not enough information. So, the mean value. If f is integrable on a to b, its average or mean value on AB is the average. The average says that I find the area under the curve and then divide it by the length. Just like if you add up 7 things to find the mean value, you would divide by 7. So that's my mean value, the integral divided by the interval of integration. So find the average value of f of x equals 2 minus x squared on 0 to 4. So the average value is 1 over b minus a times the integral from a to b of our function. This we need to use our NINT on because we don't know how to find this yet. So it's going to be 1/4 of the total integral. Use your calculator, see if you get the right value. Whoops, sorry. And for this, you should get -40 over 3, and then multiplying by 1/4, we get -2/3. So the mean value theorem, we've already done a mean value theorem for derivatives, and it said that if I find the slope from one point to another, there is some value c in between that has the same slope. The mean value theorem for definite integrals says the same thing. If I find the average value and find a point on the function that would give me that average value. So here's what it says. If I find the integral, that's the area under the curve, and divide it by b minus a, there is some point c such that this rectangle has the exact same area as the actual integral. So there is some point c such that f of c times b minus a will equal the integral from a to b of the function. That's another way of writing this. I took the b minus a and put it on the other side. The mean value times the area of the base of the rectangle equals the integral. Okay, I think it's easier to look at this way. So again, back to here. The mean value that we find times this width gives me an area of the blue. The integral is the area of the actual integral. I think that's it. Yes, we're going to do that in part 2, so that's it for this video.